Okay, what's this question? This question is given in GATE 2008 and the question was very big. So what I did is I had taken only important points and I have written them there. Only important points are represented there, and you could Google it out and see that question. Even though the question is very big, answer is very simple. Let me explain you the question. You please read it once, okay? It is worth giving it a read, and I'll just explain you what it is. So watch it. Physical address is 36 bits. So if physical address is 36 bits, it means that the main memory size is 2 power 36 and logical address is 32 bits, which means this process size is 2 power 32 and page size is 4KB, which means the size of each page in the process is 4KB, which means 2 power 12 bytes, and page table entry size is 4 bytes. So page table entry, you know it, right? And now a 3-level page table is used. Virtual address is divided as follows. Then they are saying that virtual address is completely divided, like this. Like some bits are used. There is 3-level paging. Therefore, we have to index the first level, and we have to index the second level. We have to index the third level, and finally we have to go into the page offset. So they have allocated some fixed number of bits in the virtual address for all these indices. Now, then page table entry sizes in first, second, and third levels are. So what they are asking is, I'll just read out the question. The number of bits required for addressing the next level page table in the page table entry of the first, second, third, which means actually what they are asking is, in the page table entries, how many bits are used as the frame number. That is what they are asking. So I have just written it as a small version. So you please read the question again. So what they are trying to ask is number of bits in page table entry for frame number. That is what they are asking. For frame number, that is what they are asking. You can read the question once. So how can we solve it is, see, whatever level it is, whatever the page table is, always the most important thing in the page table entry is the frame number, right? And for all the pages it will be same, right? So first thing is for sure, in all the page tables the answer will be same. The number of bits which are used to refer to a frame number is always going to be same, because main memory is divided into frames, and every frame is going to, the number of bits used to identify a frame is always going to be same for all the levels, right? So either it will be 20 20 20 or 24 24 24, which means in all the 3 page tables we are going to get the same number. So you can directly do it. So watch it. Now physical address is, they are already saying that it is 36 bits. The total physical address is 36 bits, right? And now page size is 4KB, which means 2 power 12 bytes. Therefore page offset is going to be 12 bits, right? So now I can divide the physical address into 2 parts. One is page offset and the remaining part, right? So page offset is going to be 12 bits. Then how many bits are remaining here? 24 bits are remaining. This part is going to be the frame number, and this part is going to be page offset, right? And every page table is supposed to contain 24 bits as the pointer to the next page table. Are you getting this? Therefore what is the answer? So the answer is 24 24 24. You need not do anything, and but then still this question is worth examining a bit more. The reason is they explained it in this way. See, answer is this: whenever you have multi-level paging, all the levels of the page tables will contain the same size or the same number of bits used to represent the frame number. Okay, that is for sure. And how can you find out the frame number? From the page size, from the physical address, you can find out the page. Okay, if you didn't understand how I did it, again let's examine this in one other way. See, since the physical address is 36 bits, then what is the size of the main memory, or what is the physical address space? Both are same, right? Main memory or physical address space is 2 power 36 bytes. Nothing is given here, therefore assume that it is byte addressable, right? That is how I got main memory size as 2 power 36 bytes. And then the page size is given as how much? Page size is given as 4KB, right? So which is nothing but 2 power 12 bytes. Now if the main memory size is this, and if it is divided into pages, each of size 2 power 12 bytes, then totally how many frames will be there? Page size or frame size both is same, right? Then we can write actually main memory size or physical address space equal to number of frames into frame size, isn't it? Therefore, what is the number of frames? Number of frames equal to physical address space divided by frame size. How much is physical address space? Physical address space is here, 2 power 36 divided by frame size is 2 power 12. Therefore, we get 2 power 24, right? So, if 2 power 24 frames are present totally, how many bits are used to represent, or identify each frame? 24 bits. Therefore, these 24 bits have to be present in every page table, because every page table entry is pointing to one of the frames in which that particular page of the next level is present. Got it? That is how we got it. Fine. That is how the answer is 24, 24, 24. But anyway, we shall examine this question, with using the given data. That given data is not required in order to solve this. They need not mention anything about how they are dividing this virtual address. I don't know why they gave it. I think they are confused. Anyway, let me show you what is the meaning of the question they are talking about. They are saying that 30 to 31, which is 2 bits, are used as the index into the first level page table, and then 21 to 29, which means 9 bits are used as the index into the next level page table, and then 12 to 20, which means again 9 bits are used as the index into the third level page table, and then finally 12 bits are used into the 0 to 11, 12 bits are used into the to access the outermost the actual page offset. So what does it mean? If the outermost page table or the first level page table, here see, always this initial part is generally used as the index into the outermost page table. Therefore, first level page, if they are talking about first level page, they must be talking about the outermost page table, because when you divide the virtual address like this, it is a convention that the most significant bits, they go into the outermost page table, and next level, and finally page offset, like that. Now watch it. Now they are using 2 bits to index into the outermost page table. So if they are using 2 bits to index into the outermost page table, how many entries or how many pages or how many entries do you think will be present? If I'm using 2 bits, then how many entries will be here? 4 entries, 2 power 2. Therefore, the outermost page table will contain 4 entries, right? So 4 entries will be coming out of this outermost page table. Therefore, in the next level page table, how many pages will be there? Totally 4 pages will be there, right? And in order to index into one of the page table, 9 bits are used. So since 9 bits are used to index into this page table, right, how many entries would have been present? 2 power 9 entries, right? Therefore, the number of entries that are coming out of this one are going to be 2 power 9. So totally 4 pages, and each page is giving out 2 power 9 entries like this. So how many entries would be completely coming out of this here? It is completely 4 into 2 power 9, and each pointer is going to point to a page in the next level, right? Therefore, in the next level, how many pages will be present? The total number of pages present here will be equal to number of entries coming out, which is nothing but 4 into 2 power 9, right? And each one, right, and again in the next level 9 bits are used, which means each one is going to give out 2 power 9 entries, right? So if I write like this, each one is going to give out 2 power 9 entries, right? So in total, how many entries will be coming out if each page is going to give out 2 power 9 entries? Totally there are 4 into 2 power 9 pages, and each page is going to give out 2 power 9 entries. Therefore, it is going to be 4 into 2 power 9 into 2 power 9 entries are coming out finally out of all the 3 level pages. And now each entry is going to refer to one page of the process, right? Therefore, finally the process contains these many pages. So how many pages? 4 into 2 power 9 into 2 power 9 pages are present, isn't it? And we know that each page size is 2 power 12 bytes, right? Therefore, this must be the size of the process. Now just check it. It is 2 power 2 into 2 power 9 into 2 power 9 into 2 power 12, which is nothing but 2 power 32. Yes, we got it. So that is how 2 power 32 virtual address space is represented. But actually they did something wrong here. They could have even done this in 2-level paging. See, they are saying that page table entry size is 4 bytes, right? So watch it. See, now what has happened is the blunder here is, see, the outermost page table, what is the size of it? There are 4 entries, right? And each entry size is 4 bytes. Therefore, page table entry size is already given 4 bytes. I don't know why they gave it. Okay. So anyway, since they have given it, 16 bytes is the size of the outermost page table, and in order to save this, one frame will be completely wasted. So one frame size is 4 KB, but in that we are putting only 16 bytes. That is wastage, right? And let's look at this level. In this level, each page is going to contain 2 power 9 entries. Why? Because we are using only 9 bits. Therefore, 2 power 9 entries are present, and size of each entry is 4 bytes, right? Therefore, it is 2 power 11 bytes, right? Actually, the size of the frame which is used to hold this page is going to be 2 power 12, but we are using only 2 power 11, which means even though each page is going to be loaded in a frame whose size is 2 power 12, right, we are going to load only 2 power 11 page. Therefore, only half of it is wasted, half of the frame is completely wasted, right? So the same thing here. Here also each page size turns out to be 2 power 11, right? Each page in this page table turns out to be 2 power 11, but actual page size is 2 power 12, right? So again here half of it is wasted. So this entire organization of using 3 levels of page table is waste. Let's see what we could have done better, what they could have done better. See, this entire thing is not the part of gate question. Gate question is over, that's it. But I just wanted to analyze what mistake they did. Now, they are saying that virtual address is 2 power 32, right? See this. Now they are saying that virtual address is 2 power 32 virtual address space, and the page size is 2 power 12. Then how many pages do I get? I get 2 power 20 pages in the process, right? And now page table 1 size will be equal to 2 power 20 entries, and size of each entry they are giving it as 4. Therefore, 2 power 22 is the page table 1 size. Now, if I divide this page table 1 size into many pages, how many pages I get? Right, into pages I get 2 power 10 pages. Therefore, page table 2 size will be 2 power 10 into 2 power 2. Why? Because these many pages are there and size of each page is 2 power 2. Page table entry is 2 power 2. Therefore, it is going to be 2 power 12, which is 1 KB over, right? Finally, the page table 2 is able to fit in just one page, which means we could have used only 2-level paging. How is it possible? 12 bits are used for page offset, and next 10 bits are used for page table 1 and 10 bits are used for the outer page table, right? So using these 10 bits, I could refer to one of the 2 power 10 entries of the outermost page table. Therefore, how many entries will be coming out of this? 2 power 10, and each entry will be referring to the one page of the next page table, and each one is indexed by 10 bits. Therefore, from each one of this 2 power 10 will be coming out. So out of this, totally how many indices will be coming out? 2 power 10 into 2 power 10, which is nothing but 2 power 20. So 2 power 20 indices will be coming out. Therefore, each one will be representing one page. So finally, how many pages are present in the process? 2 power 20 pages. And what is the size of each page? 2 power 12, which is going to be 2 power 32 as the virtual address space. Even 10, 10 and 12 is a better organization. Instead of doing it as 2, 9, 9 and 12, what they did is, they did this. 2, 9, 9 and then 12, and they have underutilized the pages here. But when we do this 2-level paging, I have completely utilized it. The size of this page is 2 power 12, which means exactly the page size given, and every page in this level is also equal to 2 power 12, exactly the page size given. This would be a better organization. This is completely a waste of time because we have 3 levels of paging. That is obviously 3 levels of reference is required, waste of time and again waste of space. We are not completely utilizing the page size, right? Which means we are not completely filling up the frame. Got it? So this is a better organization. Anyway, this part is not required for solving the question. Always remember, in multi-level paging, all the page tables will contain same size entries, right? Page table entry will be same, and even the frame numbers present inside the page table entry, that will also be the same. Okay, fine.